is Sha Zhou. Sha Zhou, are you ready for your talk? And
okay, can I share my screen?
Yes, please, go ahead.
Stop sharing the screen.
Can you stop sharing?
Can you share your screen, or I can share the screen? Okay.
Oh, sorry. Could you see my slides or the presenter's view?
Yes.
Okay. Hello, everyone. I'm Sha Zhou from Beijing Normal University. I would like to talk about our method on evapotranspiration partitioning from coupled carbon and water fluxes. So terrestrial evapotranspiration ET is a key component of the global water cycle. Yeah, it includes plant transpiration and evaporation from canopy interception and soil water. To improve our understanding of this transpiration and evaporation processes, it's crucial to accurately estimate them at the ecosystem scale. So many techniques have been used for partitioning ET into transpiration and evaporation, but the proportions of the two components over ET are still debated. So in recent years, several new ET partitioning methods were proposed by making use of observations of carbon and water fluxes from global anticurrent sites. The fundamental idea is to partition ET based on the coupling of carbon uptake and water loss through plant stomata, as represented by their ratio water use efficiency, WE. So next, I will briefly introduce our UWE method we proposed in 2016. So at the leaf level, WE is defined as the ratio of carbon assimilation A over water transpiration T. So combining this WE equation with the optimal stomata conductance model, we propose the concept of underlying water use efficiency, UWE. It's defined as a ratio of A times square root of VPD over TA at the leaf level. And essentially it depends on atmospheric CO2 concentration C and marginal water use efficiency lambda. This lambda is generally assumed to remain constant for a uniform ecosystem, and UWE is also expected to be constant at the leaf level as well as the canopy level. Therefore, variations in the observed ecosystem UWA can be attributed to the variation in ET relative to transpiration T. And the transpiration ratio T over ET can be estimated as the ratio of ecosystem UWA over canopy UWEP. But how to obtain this canopy UWEP? When soil evaporation is negligible, T equals ET and the observed UWA equals UWEP. Alternatively, we assume T equals ET. Sometimes during the growing season, the UWP is approximately estimated as the maximum UWA, or the upper limit of the regression slope between GP times square root of VPD and ET, which can be obtained using the 95th quantile regression. This UW method is very simple with only one parameter, it's UWEP. If UWP is estimated accurately, the UWE method can be used to partition ET into transpiration and evaporation continuously at varying time scales using flux tower observations. However, there may be uncertainties in the estimation of UWP at some sites. This UWEP is derived from the optimal stomata conductance responses to VPD. If stomata conductance doesn't respond linearly to square root of VPD, or if the marginal water use efficiency lambda is not constant, UWP would be time varying. Another uncertainty of the UWP estimation comes from size when T is always less than ET. For example, sparse vegetation or wetland size. So our UW method is more appropriate for forest, grass, and agricultural ecosystems with relatively high vegetation cover. With long-term continuous estimates of transpiration and evaporation and global flux tower size, we could further upscale them to regional and global scales using machine learning techniques. These site level and upscaled estimates of transpiration and evaporation can also be used to validate, constrain, and improve remote sensing and land surface models. The remote sensing observations, such as solar-induced fluorescence safe, may also be used to monitor transpiration by establishing the empirical relationship between safe and canopy transpiration. So that's all for my presentation. Thank you all.
Thank you, Sha Zhou. So next up is Todd Scanlon. So Todd, could you share your screen?
Sure.
Yes.
All right, can you see my presentation okay?
Yes.
Okay, flux variance similarity partitioning in 5 minutes. So this theory goes back to an important paper by Hill in 1989. Who said that an implication of Mona-Nabokov similarity theory is that we would expect to see a perfect correlation between any two scalars, either a perfectly positive or perfectly negative correlation. So is this true for water vapor and CO2 concentrations? So in other words, could we take a half hour's worth of high frequency data, plot the CO2 concentration versus the water vapor concentration? Would there be a perfect correlation? And the answer is no. For a couple of reasons. There's differences in the source sink distributions of the water vapor and CO2 sources, and also the magnitudes are different and they're being driven by distinct processes. So a better approximation to make is to apply similarity separately to stomatal exchange and non-stomatal exchange. So it's a more precise application of similarity theory. So we could take our fluctuations in the CO2 concentration and divide them into fluctuations due to photosynthesis and fluctuations due to respiration. We could take our fluctuations in water vapor and divide that into fluctuations due to transpiration and fluctuations due to evaporation. And then we apply similarity to the stomatal and non-stomatal components separately. So the correlation coefficient between the stomatal exchange should be perfectly negative. And the correlation coefficient between the non-stomatal exchange should be perfectly positive because they're both sources to the atmosphere. And then fluctuations caused by photosynthesis would scale to fluctuations caused by water vapor through the water use efficiency. So originally the mathematics involved in this approach were admittedly kind of clunky, but they have improved over the course of a number of papers, especially the Palatella et al. Paper and Todd Scanlon et al. 2018. And then this paper that came out a couple of years ago simplifies things even further. And so we have this algebraic solution to solve for the ratio of T to ET shown by this equation. And all these things basically are measured variables, everything except for the W that you see here. So we have the covariances between the vertical wind speeds and the scalars, and then the covariance between the scalars, and then the variances of the scalars. Those things are all measured. So water use efficiency has to be estimated. That's the only unknown really in this approach. So how is water use efficiency estimated? Easy way to do that is through a gradient basic approach. We have to have some knowledge of how the internal CO2 concentration changes with respect to ambient CO2 concentration and perhaps vapor pressure deficit. Also some optimization methods that are a possibility, and this was published in this paper from a couple of years ago, using a Cowan and Farquhar approach, looking for this objective function being maximized and assigning that as the water use efficiency. So does this approach work? I think this is a good example from the Scanlon paper in 2010, starting with a field with just a few corn stalks to a fully grown field over here. You can see the measured water vapor flux over time. And this is partitioned in transpiration. You see the ramping up over the growing season. And the direct evaporation, you see these ramp patterns here after every precipitation event. One of the diagnostics is if the cumulative evaporation follows the time to the 1/2 rule, and it does, with a desorptivity, what you'd expect for a soil of this particular texture. If you look at the transpiration, it doesn't follow that, nor should it, because it is being driven by not the soil physics, but by the atmospheric demand. And then there have been other papers that have used this approach, and some have shown some good results, some have shown some okay results. There are probably other papers that were not published because this approach didn't work for whatever reason. But these ones compared it with independent measurements. So some advantages of this technique: it just requires standard eddy covariance measurements. It's conceptually simple. It operates at sub-hourly timescales. And this technique isn't dependent upon net ecosystem exchange partitioning, which has some of its own issues. And then some disadvantages: probably the main one is that it's sensitive to estimates of the water use efficiency. You do need to apply high pass filtering of the time series because we want to focus on the exchange eddies and not kind of the ABL scale, large scale eddies. So you can't just use like an Eddy Pro output, which gives you those covariances and variances. You probably should apply some high pass filtering. Mixed vegetation is problematic. There's only one water use efficiency. So if you have a savanna that's C3, C4, theoretically it can be done by extending the mathematics, but it could be problematic. And then eddy covariance data itself can be noisy. We know that when computing fluxes, when you pass it through this framework, the results that you get can sometimes be noisy. Not so much in the ET partitioning because it's constrained by the total ET, but more on the CO2 partitioning because that's unconstrained. So that's the overview. Thank you.
Thank you, Todd. Next speaker is Russ Scott. And Russ, are you ready for your presentation?
Yeah, I think so. Let me share the screen. Okay, can you see that fine? Hopefully you can see the slide. Oh, good morning or good afternoon, everybody. Thanks for coming today and listening to these. I'm really enjoying these exciting talks and interesting applications and looking at evapotranspiration. So this is just an overview of one of the methods that we came up with recently to partition ET based on long-term flux measurements. Okay, so just to get you oriented to the sites, these are dryland sites, and here we have a summer growing season where the rains don't start until around July or so, and then in July the plants respond and start to green up, and then kind of peak in LAI around August, and then start to brown down in September and October. And you can see here that just the long-term evapotranspiration, peaks before the photosynthesis, mainly because as that summer rains start, you have more, the evapotranspiration is immediate, whereas the plants take a while to respond. So this technique was, whoops, that's not gonna work. Okay, so this technique was motivated by our previous work where we were just looking at the relationship across sites of GEP and ET. And what we were finding was these non-zero intercepts for the evapotranspiration where when GEP equals 0. And so we were hypothesizing that this represents a certain amount of abiotic evaporation in the system. And so when we wondered could we use this technique on say a monthly scale to estimate the evaporation, both kind of long-term evaporation at our sites where we had multiple years of data. And so what I plotted was for this site, the shrubland site, I plotted July monthly averages of GEP and ET, August, September, and October. And what we found is that a good linear relationship between those two and kind of consistent linear relationship across all months but the y-intercept went from quite high to quite low at the end there. And if we use this as an estimate of evaporation and we take our average ET over the time, we can compute an average T to ET ratio for each one of these months in the season. You see that it went from very low to pretty high, kind of peaking in August and September when the vegetation peaks, and then starting to decrease again as the system browns down. And we tested this at 4 other nearby sites with different vegetation composition. And we found the same consistent pattern of July having the most evaporation, October having the least, that they, as well as constant slopes with different y-intercepts. And what we've also found is it seems like this method works better at drier sites, probably because we get this fuller range of GEP or GPP across the years. So we're not extrapolating from very large values way out here on high GEP and high ET, and then they're trying to extrapolate down to a y-intercept. So you can see that each one of these sites has months and years where these values are quite low. So you get this nice linear regression that is not extrapolated far to get the y-intercepts. I think maybe that's why it works better. And then if we look across those 3 sites, we found again that T to ET kind of peaking in July and August and September, and then staying kind of high even though the system starts to brown down. We think that's due to just the number of rainy days as you get later into the growing season. The canopy is also not getting wet as often. So and the soil is not getting wet as often. So the evaporation is also decreasing. We did another study where we compared a dryland grassland site with a woodland site that has access to groundwater. They're located very close to each other, but one's located down in riparian bottomland area. And we compared our technique at S17 versus the Zhou 2016 method, Jacob Nelson's 2018 approach, the T algorithm, and Lee 2019 approach. And you can see at the grassland, they all had a very similar seasonal cycle. These are monthly means. And with the site, with the different methods not differing by more than about 10% or so on average. So consistent seasonal cycle. And then at the woodland site where our Scott and Biederman method didn't work so well, again, because of probably the high values. But the two approaches, the Nelson and the Lee, agree quite well with the seasonal timing compared to the Zhou. And I think there might be some limitations of the Zhou at this high transpiration site where you're using this 95% regression method, and we think that it might be too stringent of an approach. So there might be a lot of periods greater than, more than 5% of the time that T is equal to ET at the site. And so that's going to kind of drive down the estimate. And then what we also found, that, water availability really controls this T to ET. There's less variability at the woodland site. There's kind of this unimodal type behavior that peaks in the dry period before the rains start. Whereas at the grassland that's dependent on rainfall, there's this bimodal relationship for T to ET, where T to EP peaks in a kind of a spring growing season and a summer growing season. We also looked across the years, the 15 years that we looked at for this study, and we found that T to and ET was generally increasing across the years for the grassland site as water availability increased or precipitation increased, whereas at this non-water limited site with access to groundwater, T to ET was quite consistent. And that's it for me.
Thank you, Russ. So we have our last speaker, Lixin Wang. Lixin, are you ready for your talk?
Yeah, let me share my screen first. Can you all see my screen in the presenter mode?
Yes.
All right, thanks. So hello, everyone. Thank you for being here. It's a great pleasure to have the opportunity to share with you some of the thoughts about using isotopes doing ET partitioning. So hopefully that will help simulate some discussions. So this is a quick motivation of ET partitioning. Previous speaker already touched on this from different perspectives. So basically, we know there is a large uncertainty in ET partitioning. So we know vegetation play a major role in ET partitioning, but when you actually synthesize the data of all the field measured ET ratios across the field scale and under the same leaf area index, there is actually wide range of ET partitioning. So that's actually motivate us to actually doing more measurement from different environment, different systems. So in terms of isotopes, the ET partitioning principle is actually quite straightforward. We have a 2 stable hydrogen isotope and a 3 stable isotope form for oxygen. So there are multiple forms there. So we can use that to actually as our advantage to do the ET partitioning. So the key assumption here is that we know vegetation water use doesn't actually change isotope signature. So that's why transpiration signal is very similar to the source water. But the evaporation actually is much lower or much lighter than the source water because of the physical fractionation. So evapotranspiration will be somewhere in between. So basically that means you can quantify the evapotranspiration isotope signal for 3 components. Then you can just simply using mass balance to do the ET partitioning. So this principle has been there for more than 30 years. Really the development come into place when we have the laser-based instrument. We can actually measure the 3 numbers in the field like in a more straightforward way. So because we have a higher and higher precision for the laser-based instrument, and building on the laser-based instrument, we can actually quantify the isotope composition of different numbers like transpiration, evaporation, evapotranspiration. Here is an example of using a chamber-based method coupled with a laser instrument to measure transpiration signal. So we can actually using that to capture very fast response of transpiration signal, responding to, for example, vapor pressure deficit, responding to soil moisture change or lighting change. So you can do that in a very short time scale, like in the matter of minutes. So, building on this, we can then, using isotope to do ET partitioning as very different environmental settings. For example, this one, we did this in Arizona in greenhouse, basically, like we can change woody cover and look at the changes of ET partitioning. And also we can, using that in the field, like look at the changes of ET partitioning in responding to warming. So here we can see, after warming the system, you can see there are increase in ET partitioning, using the isotope-based approach. And also we can do that in a more like a pure setting, like a pure environment, like a natural setting, like a kind of a agriculture field. So in this one, we my student Michelle Lu and we did the field observation in California in an agriculture station. So looking at the biofuel production on ET partitioning. So we can do that, but the key message I want to point out here is really the additional advantage of using isotopes. So we know if you actually after irrigation, if you left the field like untended, so the isotope signature should become higher and higher for both evaporation and transpiration, because the water will become more and more evaporated. The leftover will become more and more heavier or enriched. So, but what we saw here is as time goes by, there are initial increase as expected, but then you actually saw decrease. So what basically that means, vegetation actually can redistribute the water from a lower layer to the upper layer actually to support the water use. So things like this is a kind of an additional advantage of isotope. You can not only doing the ET partitioning, but also you can actually try to understand the drivers of ET partitioning. So along the same line, we can do things like in forest. This is side from Indiana. So we're basically looking at the oak and the maple trees. How do they actually utilize water to support their evapotranspiration? So we can use isotope from the top of the canopy. That's more logistic challenging, but it's feasible to do. So you can actually look at where they get their water from. So that's kind of the advantage of isotope. You are not only tell ET partitioning itself, but also you can in a way understand the driver of ET partitioning. So in terms of challenge, so that's different from the previous method the speaker talked about. You can utilize the flux measurement directly to do the ET partitioning. For isotope method, you have to, for most of flux tower, you don't really have that. You have to build on your own. That is definitely a logistic constraint. It sometimes not super straightforward. But also from a scientific point of view, for ET partitioning using isotopes, you have to be able to measure the 3 end members all correctly. So, and also we know, one of the challenge for ET partitioning is actually the ET isotope signature. So that's actually contributes the largest uncertainty in terms of whole ET partitioning uncertainty. So, in terms of this method, it is still an open question for the community to how to minimize the uncertainty, improve the accuracy for this. So yeah, that's all. And thank you all. And hopefully that will help simulate some thoughts about different methods.
Thank you, Lixin, and thank you all guest speakers.